In this lecture, we're going to talk about Le Chatelier's principle. This looks at reactions that are already at equilibrium. So we've mixed reactants together, we've given it some time, and we've noticed that the concentration of our reactants and products has stopped changing. This means the forward and the reverse reaction rates are the same now. And I kind of think of it as the reaction being done, even though we don't have only products or reactants. So Le Chatelier's principle states that when a stress is placed on a reaction at equilibrium, that system will respond by changing the rate of the forward or the reverse reaction to relieve the stress. Basically, if a change occurs after the reaction's at equilibrium, then the reaction will either form more products or reactants to try to reestablish that equilibrium. So if you push it out of equilibrium, it'll find a way back to it. It's kind of like those clown punching bags that you hit it and it's filled with air and it pops right back up. Those are reactions at equilibrium. So some possible disturbances to it or things that could change the reaction once it's at equilibrium include concentration changes, so increasing or decreasing the amount of a reactant or a product, or temperature changes, increasing or decreasing the temperature, or if you have a gas phase reaction, changes in the pressure or volume. And now, we haven't talked about gases yet in this class, so we are not going to cover pressure and volume changes that take place. And we're going to just focus on concentration and temperature. So let's consider this reaction between hydrogen and iodine. Let's say it's at equilibrium. So I have the same amount of reactants and products. If I were to increase the amount of hydrogen that I have by adding more once this is at equilibrium, I will now have a lot more of my reactants, right? I'll have increased my concentration of reactants. Remember, reaction rate, if my concentration goes up, the rate of my reaction goes up. And so if I now have more reactants, that means my forward reaction rate right here, that's going to increase. And it's going to increase and form more products until we reestablish that balance, that ratio of our products relative to our reactants that's described by our equilibrium constant. And so once we get back to this magic ratio, then the reaction will be at equilibrium again. So we describe this response as an equilibrium shift. So this is saying that it's shifting. You can use an arrow like this. We call it shifting to the right or shifting towards products, or we can use the language that will form more products to reestablish equilibrium. There's a lot of ways to describe this, or a lot of language around it that could possibly be used that you'll see there with different resources. So let's look at another change to concentration. Let's keep focusing on this hydrogen. What if we removed hydrogen? And so we saw that concentration of hydrogen decrease. Well, now I've decreased my concentration of hydrogen. And if I decrease concentration, I decrease the rate. So that means the rate of this reverse reaction is going to decrease. Or sorry, forward reaction. That means I'm going to form more reactants to reestablish equilibrium. That magic ratio between products and reactants. And we call this a shift towards our reactants is one way to say it. Another way you might see it written out is a shift to the left as well, because we'll see more of our reactants form from our products to make equilibrium happen again. Now let's change the concentration of a product. So if we add hydrogen iodide, we'll increase the concentration of our product, right? So if we've increased that product concentration, then we can expect the rate of the reaction of hydrogen iodide decomposing to increase as well. So that's going to increase our reverse reaction. And so we'll see that our equilibrium is going to actually shift towards our reactants. We could say that it's going in this direction or shifting left in order to reestablish equilibrium. We'll form more of our reactants to get back that balance. And if we decrease hydrogen iodine, if that concentration now is lower after it's been at equilibrium, then we're going to need to form more of those products in order to actually reestablish equilibrium. So in this case, we're going to see an increase, decrease in the reverse reaction. Because we have less of our products able to collide and form reactants. And so that will decrease until we've built up a larger amount of products that will be able to maintain the earlier equilibrium rates. And so we'll say that this will shift to the right. Or that it'll shift to form more products. So what happens if we change temperature? Let's review that next. There we go. Sorry, computer's being sluggish. So this is going to depend on whether or not a reaction is endothermic or exothermic. So let's look at an endothermic reaction first, right here. So in an endothermic reaction, our heat is what we consider a reactant. This is the type of reaction where we have to input heat for the reaction to take place. So we can think of it as a reactant, and we're going to treat it like a reactant. So if we increase temperature, we are increasing our heat, which is increasing the concentration of one of our reactants, because our heat is our reactant. And so the reaction will reestablish equilibrium as if we increase the nitrogen or the oxygen, one of the reactants. And so we'll see a shift to form more products, or a shift to the right. Now, if we decrease our temperature, we are decreasing the amount of heat in our reaction, which is essentially decreasing the concentration of one of our reactants. Now, if we do that, we kind of have to backfill. We don't have enough reactants, so more of our products will form reactants. We'll see a shift to the left towards our to form more reactants. So for temperature changes with Le Chatelier's principle, it's critical that you first identify if you're working with an endothermic or exothermic reaction, because that'll tell you whether or not to think of heat and temperature as a reactant or a product. And then you can follow the same guidelines that you used for reactant and product concentrations. So let's look at an exothermic reaction. Here's one with sulfur dioxide and oxygen forming SO3. So in this case, it's an exothermic reaction. These are the ones where we release heat as the reaction proceeds. And so heat is going to be a product. So if I increase my temperature, that means I'm increasing the heat in the reaction. I'm really increasing the concentration of one of my products, and that is the product heat. So if I do that, then I'm going to have all these extra products that are going to shift, and equilibrium will shift to the left so I can form more reactants to reestablish that equilibrium. And if temperature decreases, I decrease the heat in the reaction, which is just like decreasing a product. And so I'm going to shift right towards my products and form more of those to reestablish equilibrium. So this will be the opposite of our endothermic reaction, but the strategy for solving it is the same. So here's a summary. So here we have our endothermic reactions, and here we have, our exothermic. Here's our exothermic reaction. You can tell because heat is a product. And here heat is a reactant. And so these are our endothermic reactions. And so we have a summary. If we increase a reactant, or if we increase a product, we can see that we're going to shift our reaction away from whatever we increased. So if we increase something, we're going to form whatever's on the opposite side of the arrow of it. And if we decrease a reactant or product, we can see that we shift our equilibrium to form more of whatever we decreased. So if we reduce a reactant or product, we're going to try to backfill and fill in more and make more of whatever we got rid of. And so that's a pattern that will hold for temperature 2 for exothermic and endothermic. So let's look at an example together. So we've got a reaction where NO2 is decomposing to NO and oxygen. So if we add more NO in our reaction, we're going to increase the concentration of NO. NO is a product, so we're going to increase the amount of this product. That means we're going to have more of these products that can collide, and so we're going to see that reverse reaction increase. So as we do that, equilibrium will shift to form more reactants in order to reestablish it. Now, if we decrease the temperature, we're going to be decreasing the amount of heat that we have in our reaction. So now this is going to go down. And when we decrease the amount of heat, we're decreasing a reactant. And so we are not, we'll see this arrow for the forward reaction, this rate decreases as well. And so that means that we're going to have more opportunities to form reactants from products until the concentration increases on our reactant side and we can reestablish equilibrium. So we're going to see equilibrium shift to form more reactants as well. Our next one, we're going to remove oxygen. So here's our oxygen right here. We're going to decrease our reaction concentration of oxygen. So if we do that, we're going to see a decrease in the reaction rate moving in the reverse direction. And so we're going to see equilibrium shift to form more products. this will shift this direction. These reactant ones were shifting this direction to the left. Okay, let's look at our last one. We're going to remove NO this time. Here's NO. So we're going to decrease our concentration of NO. So just like with the oxygen, we're not going to have as many reactants now, so we're going to see a smaller rate of our reverse reaction. So again, equilibrium will shift to form more products. And that's the interesting thing. Regardless of which product is decreased, we'll see more products form to reestablish equilibrium. So I don't have to decrease both, just one, to see that same equilibrium shift. All right, that concludes our lecture on Le Chatelier's principle.